How's it going? MoNaCo here. Our seventh and second to last video in our Kinetics unit. We are focusing on the concept of entropy in this particular video. Entropy is a new term for you. You may never hear it outside of a chemistry or physics classroom, but entropy is a driving force for the universe to work. So define entropy and determine if entropy increases or decreases for given reactions is what we're going to be doing in this particular lecture. Can you measure how disordered something is? Like, think of your room. Is it super neat or is it super messy? Or think of your laundry pile. Do you fold your laundry so you can put it in the dirty laundry pile? Think about that. Disordered or ordered. Disorder, crazy, chaos, random. Ordered, nice and neat, sequential. So yes, we chemists have named the phenomenon for measuring disorderedness, entropy, and the universe likes it. The universe likes things to be crazy, random, and disordered. Overall. Entropy, the term that we use is delta S. It's the degree of randomness or chaos or disorder or messiness in a system. So nature tends to proceed to a state of greater entropy or disorder. The more order you have, the less entropy in your system. So the more you're asked to line up in single file and prepare for scanning in the morning, the less entropy is in the system. Nature says, just get in the building as fast as possible, don't line up, just go. That's why nature likes crazy randomness to order. The less order you have, the more entropy in your system. So until you're told to line up and get through scanning properly, you have very much a lot of entropy. Then the security folks say, hey, get in line, get ready, less entropy. They're ordering the system. What physical state of matter has the highest entropy? So the highest craziness, randomness, and disorder. The most crazy. I hope you said gas, because those particles are all over the place. They're not lined up in neat rows. So going from solid to liquid to aqueous to gas, you'll experience increased entropy. So as we go from solid to gas, each step along the way, the particles are becoming more and more random, more and more entropy is being added to your system. And the universe, in general, likes that. Let's check out the next one. Particle diagrams to illustrate each of the following phases. Solid. You know how the deal is. 9 particles in the center, bottom of the beaker, square box shows us that these are highly organized particles. Liquid. We like to make sure that they are touching both sides of the bottom of the container and that they kind of try to fill the shape of the container, but they're not all over the place. They're on the bottom. Liquids fill the bottom, then to the top. Aqueous. Aqueous is unique because you have to show that there's water involved with little boat waves. And then you have to put the particles in there as if they were dissolved, kind of hanging out. So they're in the water, but they're not in the air above the water, and they're all over the place, touching all the different walls, all that kind of business. They're dissolved, floating around in there. Now the gas phase is where you have to make sure that when you draw them, you put a particle on each wall of the container, and then you kind of fill them all in, otherwise completely randomly. Okay? Now I have coincidentally, yeah, that's random now. I was starting to make a pattern, but I had to divvy it up, because if it was patterned, it would be ordered, and that isn't what we're trying to show. Entropy increases when a compound is broken down. So if this were a compound, and I've broken it apart into the things that made it, I've increased the disorder of the system. Entropy decreases when a compound is created and bonds are formed. So if this was particle A and particle B, they're now more ordered, so entropy just decreased and created a new bond. That little click sound. So for the following, determine if there's an increase, decrease, or no change in entropy. So we have to look and decide, are things getting more crazy, or are things getting simpler and more ordered? The things that you got to look at most when we're talking about these things are the phase codes. Okay? And to see if a reaction is breaking things up or creating things. So there's a few different layers of thought here for your logic here. So if we take a KClO3 solid, and it makes 2 different things, one of which is a solid and one of which is a gas, we've broken something apart and made a gas. So we could say that entropy increased in that particular scenario. We are more crazy, random, and disordered. Now here in the second one, we have H2O liquid becoming H2O solid. So there aren't anything breaking apart or coming together there. It's only a phase that's changing. So we take a liquid and turn it into a solid. Let's make sure our liquids are kind of random and our solids are super organized. So I would say that entropy decreased in this scenario. The order of the system increased, so the crazy randomness and disorder decreased. It's almost inverse. You have to think about it like that. Next example. Nitrogen gas and hydrogen gas making ammonia gas. So I have two things coming together to make one third thing. All of them are in a gas phase, so we have to just look at the fact that it's two things coming together to make a more ordered third product. So more order means that entropy decreases. Okay? One more and then you're on your own for the rest of them. Sodium chloride salt, solid, becoming sodium aqueous and chlorine aqueous. Solid versus aqueous. Just look up at the chart here. Solids are super ordered. Aqueous are almost crazy random and disordered. So entropy is increasing for this scenario because those particles are getting more spread apart, more crazy, more random, more disordered. Okay? A lot of examples here. Practice these in your homework practice pack. There's plenty more practice in the practice pack. Note, if all the states are the same, count up the number of molecules on each side. More to less molecules equals decrease in entropy. Less to more is an increase. So pay attention to the note, figure it out, problem solve it. It's logic. Use the pictures, use the definitions to go. So at this point, you should have the basic understanding of what that entropy term means. Randomness, chaos, disorder. And use a chemical reaction to identify if entropy increases or decreases. Remember, pay attention to those letter phase codes at the end because that could be the secret to figuring it out. No practice pack? Talk to you in class. Thanks for watching.